number of transfer units and the height of transfer unit. So this might be sometimes confusing. So in order to illustrate to you, I will, so the problem is this goes in this way. So this is the field. So the field is actually in industry. The field is the part of the column. So in this field, actually there is an the air and the liquid part are in equilibrium, so that in such a way that the transfer is most effective. So there is that. So don't be confused that when you say about the height of the transfer unit, it's not the height of this one. It's the height. It's this height. But note that the number transfer the height of the transfer unit will also be divided in terms of the number of transfer unit. For in case, the number of transfer unit is 2. So this the height that we must get is divided by 2. So for in this problem, it's 4 feet. I think it's 4 feet. So if you have a height of 4 feet and solve, we're just assuming that the number of transfer unit is 2. So the height of the transfer unit is 2 since we divided it by 2. So we will. I will explain it later in the problem. Okay. So in this problem, we have discussed earlier that the operating line is actually solved and the equilibrium line is actually solved. But then in this problem, the equilibrium line and the operating line discussed earlier is already available. It is in figure 19.8. And I requested my classmates, so please note down where did I get the values, because you might be confused of how the solution goes, because some of these values are actually can be get through the graphs or figures in the K6 division. Okay, so let's continue. So actually the enthalpy can be determined from the wet bulb of 75 degrees. Since the adiabatic saturation temperature is just equal to the wet bulb temperature, which is given at 75 degrees Fahrenheit. Okay. So from figure 19.8, from 6th division, so we can see that earlier there is an operating line. There is an operating line and an equilibrium line. This figure actually there is a temperature and enthalpy. So to get that enthalpy at 75 degrees, we just use the equilibrium line, and for example there is or in this case 75 degrees Fahrenheit. So just do this, just put an the equivalent enthalpy at 75 degrees using the equilibrium line. Don't be confused with the operating line, since you will get a different enthalpy for that. So then you get since we already get the outlet liquid temperature and the inlet liquid temperature, so we also get the enthalpy of this value. These values will be used later. So what TB1? So what's TB1? The inlet temperature. So we get this at 90 degrees Fahrenheit or 550 degrees Fahrenheit. So actually, before we go on, so we must first get the density of the vapor, because vapor basically differs from temperature to temperature. So the first that we arrive is that we get the value of the density of air at standard temperature. So that's from CRC of chemistry. So it's 1.89. So we get the first specific volume. We get for the uniformity of the unit. So we get in cubic feet per mole. So cubic times we get okay. So this is the value. So you can see that we arrive at pound per cubic meter. But take note, a specific volume can also be determined from the unit charge. That is in McCabe also. So we can actually find it in figure figure 19.2 in McCabe station. Okay, so since once we have the density of the vapor, so we get the flow. So don't be confused about the sheet. Earlier it was discussed that the flow rate is in B, but since we have a different reference, so we get G as the mass flow rate. So for the mass flow rate of vapor, we use V and GL for the liquid. So you might be confused. Why do you use G of V and the liquid must have different flow rate? Because for instance, because earlier we have discussed that there is the spray that has a drift or windage, but in this problem, since there is only a point for a well-designed cooling tower, there's only a 0.2% loss. So it's actually for McCabe in this problem, it can be neglected. So we use a constant liquid mass flow rate for the liquid and the vapor. Okay, so we can get the flow rate by this equation. So we get the flow rate for the vapor and then the flow rate for the liquid. Okay, so we use for the area we use the 36 times 36. So just in case you get confused, what this value? Where did we get this value? So it's from the initial given. Okay, then see. So from equation 19.27, so it's also from McCabe. Then we get d delta V, the change in enthalpy in the vapor, just equal to the mass flow rate of the liquid and the specific heat of the liquid and the temperature difference in the temperature of the liquid. So by plugging in the values, we get delta V. Then again, we get the answer for the delta V. But then HV2 is not given. So to get the height and the number of units, we need to get that. So HV1 is actually also given from the figure 19.8. So from the 75 degrees wet bulb. So since as it also got the equilibrium line, we just plot and we get the value of 31. So then we get the value of the outlet air. So at the bottom of the tower, so we get the at the bottom of the tower, we have this value of the enthalpy of the outlet water, then the inlet air, then we just subtract it when we get this value. So we just get the mean of these values, then we get 12.7159, then we get the value of n. So here's the value of n, 1.7, just like what I had said before. So the pin height, so is actually 3 feet. Then we just divide it by the number of units is this. So to get the height of the transfer unit, so we get the field height then divided by the number of transfer unit, then we get the actual field height.